do want to post this for anyone who wanted to attend but couldn't later on. So just kind of as a heads up for all of you, we're going to try to get, through the Q&A as best as possible. And so I'm going to be kind of taking the lead as far as, doing problems. And then we have another instructor. In fact, I'll let you introduce yourself a little bit. And I've been answering questions for a little while here, so you can say, anything that you want about yourself. And kind of she's going to be in charge of the Q&A, and kind of we're going to be doing the class together. So go ahead, whatever you want to say.
All right, so it's nice to meet you, and I will be the one answering questions on the Q&A or chat, I guess, right?
Yep, perfect.
Yeah, and yeah, I'm happy to work with you, and then, yeah.
Let me show you guys too. So at the top here of our D2L page, under Get Help, there's an instructor list. And one of the questions that we had before class began was, when are office hours? And so I just wanted to show you kind of, if you need to reach out to either one of us, we have our email here, but you can also see that, right, I have office hours 4 to 5 p.m. It's my personal Zoom URL, so you don't go to the recitation or the lecture URL. Each instructor will use their own, just because we may have office hours happening at the same time and whatnot. And so, yeah, my office hours are Tuesday, Wednesday, and Friday from 4 to 5 p.m. And then let me scroll down here. I remember seeing you, like, there you are. And so your office hours are up to date on?
My office? Yeah, it's updated on Tuesday and Thursday. Yeah, that's right.
Perfect. Okay. Great. So yeah, and you can see a different Zoom URL and all that sort of stuff there. So the way that I like to structure my classes, oh no, my iPad said my share abruptly stopped. Let me see if I can't get this going again. I'd like to spend around 5 minutes or so kind of quickly going over the pre-class video notes that I hope that everyone took a look at before coming to class. And then, of course, we have new problems to cover. So again, the intention here is that you do watch the pre-class videos to get some preliminary understanding for the topics before coming to class, and then we're going to expand on that in class. So for 5.2, this is all about volumes, and kind of this is a continuation of our Calc 1 class here at MSU, where you did a couple of sections in Chapter 5 in Calculus 1, and then we're kind of finishing this up. So kind of, Chapter 5 is very much kind of a wrap-up chapter from Calculus 1. And then, of course, we're going to expand on that and continue through Chapter 6. And really, Chapter 7 is really where the meat begins, I would say, for the new stuff for Calculus 3. Kind of like, if you look nationally, what does really Calculus 3 involve? It really, every single class out there has the Chapter 7 stuff. And so that's going to be about integration techniques. 5.2, one of these applications for integration. So you're talking about, okay, now that you can find antiderivatives or integrate, what are some things that you can do with that, right? And so you did like area between curves in Calculus 1. And so we kind of start off with a problem related to that, because it gets used very much here when we start to do volumes. You also did stuff like average value of a function and the mean value theorem for integrals and stuff like that, that we don't really use so much. But this stuff right here, how to find really the area between two curves and integrating with respect to X or Y, you see that this becomes very useful as we try to expand this and we try to figure out how can we find volumes. And so instead of adding up lots and lots of, well, really, these are areas of small rectangles, right? It's kind of a distance, and then you do a little dy, or over here, a distance, and then a little dx, and you multiply those things together. And so you add up these areas. And when you add up lots and lots of small areas, right, you get the overall area. And you get a similar sort of storyline when you're doing volumes. You add up kind of very, very small volumes. So you have this small change in X. So really, these are like tiny, tiny cylinders, right? And then you have the area formula for a circle here. So, and remember, the volume for a cylinder is the height times the area of the base. And so really you see that area very strong here, area of a circle, this pi r squared. And so here's where you actually get the full definition, right? If you want to find volume, integrate or add up those tiny, tiny volumes. That is area times the height, right? Because that's the area formula for a cylinder, or in general, a prism. So yes, so integrating area gets you volume. And so then we get kind of there's three types of problems that you see in this section. There are revolution problems, right, where you kind of rotate something around and you have this disk method. And this is where kind of the region butts right up against the axis of rotation. You have the washer method, which is where kind of it doesn't butt right up against, so you don't get full circles, but you get circles with a hole in them. And so hence washer method. And then you have an inner and outer radius. And so there you go there. And then the final type, and so we did, of course, some example problems. And the final type is when you're not rotating at all and your area formula is dictated by something else, right? And so in this case right here, you had this two-dimensional structure, right, that you've sat down, it's a piece of paper on your table, and you've glued to it, you know, some interesting structure. So in this case, we're gluing to it squares, and the size of the squares depends on kind of how big this purple line is right here. So this is this perpendicular to the x-axis in this region. We're kind of gluing these squares. I think these are the most complicated types of problems, and so they take a little bit to get used to. Well, you saw two that we did here in the pre-class videos. You'll certainly have some in the WebWork homework, and I also have a couple for us to do today. All right, so that's my kind of quick 5-minute, ended up being 7 minutes, 8 minutes now, kind of review of the pre-class video notes. Just kind of, this is what we'll usually start the class with. I guess before I get into the new problems, let's see if, you know, what kind of questions are being asked out there. So I'll kick it over to you. Juan? I guess see it, the chat's going wild.
Too much. I can answer at the same time.
Let me maybe try to look at
because sometimes they have some like attendance, a lot of questions about the attendance.
Okay.
Yeah. Is it mandatory to attend the live Zoom?
Yeah, mandatory is such a funny word because, you know, there are certainly consequences to not attending or not, you know, doing certain things. I mean, if you skip an exam, I don't know, could you still pass the class? Probably, right? So do you call it mandatory? I don't know. Anyway, there are points associated with either attending the live class, like you guys are all doing right now, or you can watch the video that we post later. And so this is outlined in the syllabus. I believe you have 24 hours from when class ends or something like this to view the video in D2L, and you could get the attendance credit there. Just as kind of an FYI, I think the main place that we're going to be looking for answering questions is really in the Q&A. So the chat's, you know, wonderful if you just have, you know, interesting anecdotes or like things to point out and whatnot. But if you have a question that needs to be answered, please post it in the Q&A. That's where we're going to be looking. And this also has a really nice feature that you can upvote. So if someone else asked a question that you also have, then you can upvote that, and that kind of brings it to the top of our screen, and those are more likely to get answered. So please, if you would, Q&A. Is it possible to mute the chat? I don't know if there's a way to mute the chat. Sometimes I pull up so I'm on a desktop. It may really depend on kind of what device you're using. Sometimes I pull up the chat and I just kind of drag it, you know, that window to the top right corner or something like this. And then that way I don't get the little notifications, but still I can see things passing. I was confused on how we decide whether to integrate with respect to X or with respect to Y. It's a great point, and we're going to be doing that kind of, I'm going to be highlighting that in our first one, you know, coming up here. And then finally, last question, and then I'll kind of start some new problems here. I haven't taken a calculus class in 2 years. What's the best way to catch up? So I have a series of Calc 1 videos that I would recommend. I also recommend buying the full textbook. I checked earlier, someone had emailed me. So this is the full textbook. There's a link to it in the syllabus. It's like $20. And this is for Calc 1, 2, and 3. So it has all 3 of the calculus classes, all the notes and whatnot. If you buy from the publisher, I think they kind of chop it up into thirds, and they have just the Calc 1 bit, just the Calc 2 bit, just the Calc 3 bit. I think Stewart Calculus is something on like its 9th or 10th edition. So, but we're using the 7th edition, and that's why it's only $20 on Amazon. So if you can find it used, Amazon, eBay, whatever your favorite place to buy used books is, used textbooks, you can do that, and it's relatively cheap, and that would be a wonderful way as well to review for Calc 1. Okay, so let me go ahead and jump over now to our week 1 problems. So again, these are available on D2L. Let me just show, since we're recording right now, I will go here, and I just want to go back to our home page here really quick for Calc 2. And I'm going to go down, and there are a ton of very useful links here in the navigator. So just beyond the announcements, this is kind of where you get more or less everything. We're trying to accumulate lots of useful links here of things. So in particular, this is Wednesday's class, 5.2 volumes, and we're in the 150 class right now. So you can see those are where my notes are. Those are the blank notes. You can download those and print them if you'd like. And once we get class done, we'll be uploading the video and linking to it right here where we have this video link button that's right now doesn't do anything. So yes, that's where things are going to live. And you can see that I have my notes already done up through week 3. So you can get ahead a little bit. You can download my notes for weeks 1, 2, and 3, print those if you'd like to get that taken care of. Okay, with that, why don't we go ahead and start? We have a region, right? A nice triangular region. Of course, it goes to the origin right here. We have a straight up and down line making up the right side of this triangle. And then we have this key point of 2, 2. And the question is, if we were to take this region and rotate it about the x-axis, what would the volume of that solid be, right? So we're going to go ahead and take this. And basically imagine that we're gluing it to the x-axis. So we're gluing it right along here, and you take it and you spin it around really fast. That's one way I like to imagine these. We maybe use a different color here just for fun. So if we were to spin this around really fast, you would end up getting kind of these circles. And overall, you would get this kind of pyramid thing that looks like it's been put on its side. And the question is, what is the volume of that pyramid looking thing? And so one question that got brought up that I want to make sure that I emphasize kind of as soon as possible is, how do you know when to integrate with respect to x versus when you ought to be integrating with respect to y? And so I want to give you a little bit of a rule of thumb. And that is, so if it says that you're rotating about some y equals line. And so this could be y equals 0. It could be y equals 1, y equals 5, y equals negative 100, y equals anything, which is why I'm just denoting it with a little scribble. But however you want to denote y equals bleh, something, right? So if you're rotating about a y equals line, then you're going to be integrating, with respect to x. And again, kind of we go into a lot of detail in the pre-class video of why this ends up being the case. These circles right here are perpendicular to this y equals line, right? And so, and these are at specific x values. So maybe this is at x equals a half, x equals 1, x equals 2. So at specific x values, that's where you get those circles. And so that's kind of the why, right? This is a rule of thumb. This is a general rule that I'm telling you, or a theorem if you'd like. But if you're asking why is it the way that it is, well, you need to go back to the pre-class videos where we really explain it in a lot of detail. If rotating about an x equals line, so x equals 1, x equals 5, x equals negative 13, whatever you want, right? Then you're going to be integrating with respect to y. So basically, you need to do the opposite. And let me show you that even in this first problem right here, it still requires a little bit of extra thought, right? Because it says that you're rotating about the x-axis. It doesn't have an equation. It doesn't say x equals blah or y equals blah. It just says the x-axis. And so we need to remember, how can we, take these words, the x-axis, and turn this into an equation? Well, remember, the x-axis is all the places that have height of 0, right? You haven't gone up any, you haven't gone down any. They're all the places that have a height of 0. And so because of that, can anyone tell me, either in the Q&A or in the chat, what is the equation for the x-axis? Yeah, I see a lot in chats popping up. Absolutely, it's y equals 0. So because now we have the equation form of these words, the x-axis, we know that we're kind of in this first situation. We have a y equals blah, right? Y equals blah, and so we're going to be integrating with respect to x. And again, that makes a lot of sense, because as you kind of increase your step in the x direction here, you get different circles, right? And of course, we know the area formula for the circles. So again, kind of the way that you need to approach this problem is you're going to start off by integrating area, right? And you need to know, am I integrating with respect to x from some a to b, or am I going to be integrating with respect to y? And this kind of frames the question, differently. The problem, and this is just going to be a quick side note here, if you were to integrate with respect to y, and you were to take different little steps in the y direction, the problem with that is, so maybe we have y equals 0, and if you were to take a cross section here with y equals 0, you end up getting this parabola shape. And if you take, maybe at y equals 1, you get this other kind of parabola shape. And the problem is that I don't know the area formula for these little half parabolae shapes. I know the area formula for a circle, which that means, we can kind of quickly go from this one right here and say, well, the area formula, as I take steps in the x direction, this is going to be a pi r squared sort of deal. Those are circles that we have there, because that's the way that we're kind of rotating around. On the other hand, if you were to integrate with respect to y, you would need to know an area formula for different kind of these half parabolae things. And so that's not to say, that it's impossible to do it that way, but without some sophisticated computer program, or without having a great formula for exactly what these parabolas are, it would be very, very difficult. It wouldn't be something that we could do in a time setting for a homework, for a quiz, for an exam, anything like that. So this one, it just doesn't work out. Oh no, I kept on hitting back, and I erased some of this stuff. Blech. Okay, so this is the correct way to do it, in any feasible amount of time. So that being said, right, I now have, well, I guess we could do two things here. First of all, we could now figure out what our bounds for this is going to be, right? So we're integrating with respect to x. And so I need to know, what is my smallest x value and what is my largest x value for which I'm in this region. And so if I go over here, we can see that the smallest x value that I have in this region is over here at x equals 0. And the largest x value, and it's kind of been muttered up, from my sketching here too much, but it has to do with this straight up and down line right here. It's the x value. Well, we go to the x coordinate, of course, and we see that this is at x equals 2. So the smallest x value in our region is 0, and the largest x value in our region is 2. So I could say that when we go to integrate here, this is going to be integrating from 0 to 2. That's the easier problem solved. The harder problem is that we have a mismatch in kind of our variables here. We have r's and we have x's. We are still in single variable calculus. There is a class, right, Calc 3, Math 234, which is called multivariable calculus, in which you can kind of rectify, if you have multiple variables and all this sort of stuff, how do you deal with this? But in our class, we're always going to try to integrate with just one variable, right? We're doing single variable calculus 2. And so we need to kind of figure out, how are these things related? How can I exchange R's and X's? And so we need to go back here. And this is, again, kind of why the picture is so powerful here, and why I would really recommend. I know people like to try to get away from, if you don't have to draw the picture, trying to not do that and skip that step. And I understand, to try to save some time and whatnot, how that's, why you would want to do such a thing. But really, kind of when you go to the picture and you can actually see where the radius is and where are, the X values, I think this has a lot of benefit. And so let's draw it in our picture here, right? The radius is, for each one of these circles, is this straight up and down value right here, right? That radius is determining, right, how big those circles are. So these right here are all of my different radiuses. And depending on how big of a step that I take away from my origin, so for instance, if I'm down here and I just take kind of a relatively small step, that green didn't show up on top of the green at all. So if I take this, step in the X direction, right, that will tell me how big my radius needs to be. And likewise, if I take a bigger step, let's say I go all the way out here, I get a bigger radius. And so the X values and the radiuses are related. And it seems to have everything to do with this line right here. So this line right here is telling us how far out we go. How does that actually determine our radius? And so this becomes sort of a game. This is an old algebra game, right? We have a couple of points and we want to know, what is the straight line between these 2 points? And so for a straight line like this, we know that it's going to be a y equals mx plus b sort of deal. And well, our y-intercept, our b value is 0. So we get y equals mx plus 0. And then finally, we need to somehow encapsulate the slope of this line. So that's going to be the rise over the run. So we have a rise of 2, right? We go up 2 when we do a run of 2. So rise over run, that's going to be 2 divided by 2, that's going to be 1. Some of you may have just been able to look at this and say, that's, y equals x, right? We go from 0, 0 to 2, 2, that's y equals x. And so maybe you can just guess and check this, but if not, just kind of go back and rely on your algebra skills. Now, I said that we need to find a relationship between r and x, right? And I just found a relationship between y and x. But notice kind of the y value, how much we're going up and down, that is the radius. That's determining the radius of these circles. And so even though kind of classically when we did algebra before, we loved our y's and our x's, here, since the y value or the r value is this kind of up and down measurement to how far do we need to go in order to hit this line, really the r, the radius, is the y value. And so here we see the relationship between r and x. And so, yeah, sometimes I, wrestle with myself, how soon do I want to bring r into this? Because kind of, again, classically, we dealt with a lot of y's and x's when we did algebra through the first time. So at some point, need to do that swap of names, essentially. So here we have r is equal to x. So now we're going to just go ahead and swap that in. This is the hardest part of the problem, right? The hardest part of the problem is figuring out what to integrate. Now that we actually have the integral set up, remember, constants are along for the ride. So pi is just hanging out there. And when I find the antiderivative of x squared, we raise our power by 1 and we divide by our new exponent here. So we divide by 3. I need to evaluate from 0 to 2. And so, of course, when we plug in 0, it's boring. You just get 0. And when I plug in 2, we get, well, let's see, pi over 3. And 2 cubed is going to be 8. So my final answer is going to be 8 pi divided by 3 for this. All right. So I see there's a couple participants with raised hands. I'll try to call on these couple folks here, and then I'll throw it over to you, Owen, and see if there are any kind of questions in chat that have come up while we were talking here. So let's allow this first student to talk here really quick, and then we'll talk about anything else going on in chat. So let's see, I'll ask to unmute.
Here. I think there are a lot of people. Okay.
Oops. Oh, maybe I think, sorry, Aaron, someone had.
Yeah, first, sure.
Disable talking. Barshad, you're up if you would like to vocalize your question.
I didn't have a question.
Oh, okay. Why was your hand raised? Just FYI.
Oh,
Just
my
question.
bad. I didn't realize it was raised.
Oh, okay. No problem.
Sorry about that.
Not a problem at all. All right. Kayla?
Jakayla.
Jakayla, you're up if you'd like to ask a question.
I pretty much understand everything that's going on as far as what you've taught so far, but I actually just had a question about where exactly to find the class notes, like follow along with you. Like, where can I print them from?
Yeah, so the class notes are on our D2L homepage. Let me back up here a little bit. So at the very top, we have the announcements and stuff like this. If you scroll past the announcements, you get to this, what we're calling the navigator, which has like a lot of links for a lot of stuff. And so here we are, the Wednesdays class, 5.2 volumes. There were some pre-class notes that I went over for the first 5 minutes of class. And you should watch those videos and fill out those notes, and that's what I expand on. And then the class notes, here we are at the 150 class, so you can print off the blank class notes there. And when I'm done with today's lesson, we'll put the video here.
Okay, thank you.
And then Ian, you'll be the last one for raised hands anyway, and then we'll jump back to questions and whatnot and the Q&A. Ian.
How did you find where the radius is equal to x?
Yeah, that's like I said, this is kind of the most complicated bit, I would say. You need to figure out how does the x value, how far does going over in that horizontal direction influence how big of a radius for our circle there is. And so at very least, we can see from this picture that the farther away you get from the origin, the bigger the radius is. Right. And so there's kind of this direct relationship. Bigger X's give out bigger R's. But to figure out the exact relationship, this kind of hinged on this line that we had right here. This line, this is kind of where the structure stopped. And so however far you went over in the X direction, if you drew a line straight up, right, that gave you the radius of that circle that we have in our picture here. And so we had to figure out what was the equation of this line that related together the R value and the X value. And so we needed to go back to our algebra days, right? This whole Y equals MX plus B thing. Here, really our Y variable, our dependent variable, our ups and downs, right, is really giving us the radius. And so we could do R equals MX plus B. We go through the point 0, 0. So that gave us our B value, the Y intercept. And then we used rise over run in order to get the slope.
So could you also do like related rates where you could say the 2, which would be the radius, is also equal to or over 2, which is the height, which is then equal to R over X, and then solve for that because you would get R equals X or H in this case if it was the height.
Yes. So you could look at this as similar triangles here, and then use that whole ratios of the sides of similar triangles must be equal to one another. Absolutely.
Okay. All right.
Yep.
Thank you. Thank you. Yep.
So just so anyone who may have missed that, you could also set up, right, the overall triangle here is a 2 by 2 triangle. So you could say it's 2 kind of wide and 2 high. And the smaller triangle here, which maybe this is somehow changing, it still is a similar triangle. It's a right triangle and with a same angle there. And so you could say R is to X. And so then you just kind of cross multiply, and this would be another way to get to here. So yes, either way. All right, excellent. And any questions coming up in the Q&A on that we should talk about?
No.
Yeah, most people are asking about the nodes, and yeah, I think you answered the question.
Great. All right.
And I'm not sure about some people is asking use the related race to get the radius.
Okay, great. We talked about that a little bit as well. Ian brought that one up.
Okay. Yeah, someone is asking to mute the chat, but I don't know how to do that.
We talked a little bit about that. I think so. I have the chat just kind of brought up, and it really depends on the device that you have. But I have the chat brought up and just kind of running on the side here. And that way it doesn't distract me with the little notifications for the most part. And I just look over, when I want questions. yes, it's all right that you're watching this lecture, even though you're in a different section. Any of the lectures will give you the attendance credit. I found Calc 2 material considerably more difficult than Calc 1. Is that normal? I would say, yeah, if you polled people and averaged their answers, I would say Calc 2 is, more difficult than Calc 1. The other thing is that, when I've polled people in the past, in Calculus 1, I say, how many people have seen some Calculus 1 before? And, with a live class, you can just have people raise their hands. And it was probably on the order of like 80% of folks have seen Calculus 1 before. And so, yeah, that's it's certainly easier to digest material when it's the second time or third time seeing stuff. But also, I found that Calc 2, it kind of calls a lot more from our algebra skills, our trig skills. We use exponentials and logarithms, which don't seem to be anyone's like top favorites usually. And so, yeah, the topics in Calculus 2 are typically, right, if you were to, again, poll people and average the results, I would say that the topics in Calculus 2 are typically more difficult. No, there are no checkpoints after the videos. All right, I'm going to do another problem. Otherwise, we'll have this class where we only got through one problem. I'd like to now do a more difficult problem where instead of rotating about the x-axis, I have the same picture. In fact, maybe I should go ahead and copy the picture really quick. The same initial region here. So this nice triangle region that goes to the point 2, 2. And instead of rotating this about the x-axis, I would instead like to rotate it about the line x equals 3. So maybe let's go ahead and draw this. I was just emphasizing earlier about how a good sketch has a lot of value, I think. So this right here is our axis of rotation. We are rotating about x equals 3. So x equals is a straight up and down line. And so this is how we're going to be rotating it about. Let's go ahead and draw our picture, what our solid would look like. So if we were to kind of take the straight up and down bit right here, which by the way is x equals 2. It's a portion of this. Of course, this line would go on forever, right? But we're just going to take this portion of this. We're going to rotate it about x equals 3. Of course, it's distance 1 away, so it's going to make it all the way over here to x equals 4, for instance. And you get this sort of bit right here. Now, for this other slanty bit, right, you get something like this. It's going to be related to that piece right there. And so you get something like this. It's kind of like one of those cones that you see for like soccer or something like this. But it's a little bit thicker, right? It has some more weight to it. We can see though that it's not a solid, it would be like a bead or something because there's this hole in the middle. And so this is going to be one of those cases where you need to use an inner radius and an outer radius. Kind of there's two interesting things here that are that are kind of coming together to make this structure, right? It's not a solid structure like we had before. It's a structure, but there's a hole in the middle of it. Also, one thing that we could do at any time, right? We know because this says x equals 3, we're in the second situation here, right? So if we're rotating about x equals blah, so again, the big thing here is x equals something. X equals 0, x equals 5, x equals 100, but it's an x equals equation, then integrating with respect to y is going to be the way to go. So we're going to go ahead and set up our integral here. It's going to be something like this. Now that we know that we're integrating with respect to y, we can ask for what is the smallest and largest y values that are included in our region. So the smallest y value is down here at the bottom. That's at y equals 0. And the largest y value happens up here at y equals 2. So this is going to be an integral from 0 to 2. Now, in our last case, we had our region but right up against our axis of rotation, right? So again, the axis of rotation was at y equals 0, the x-axis, and the region came right up against it. And so notice whenever that happens, when you rotate this around and you get a solid, you get a full, complete solid structure. You don't have to worry about an inner radius. But notice what's happening here, kind of our region stopped at x equals 2, and yet we were rotating about x equals 3. So there's this whole gap right in here where we don't have the region butting right up against the axis of rotation. And so we get a hole. And so whenever this happens, you're always going to have to use the washer method. There's always going to be an inner radius and an outer radius. So in this case, we're going to set up the equation. This is going to be pi r squared minus pi r squared. And you have to be a little bit careful. I know it's tempting to shorthand it like this, But if you do, right, you could be confuse yourself or someone else into thinking that these R's are the same. They're different R's, and so different textbooks and whatnot to denote these differently. In my in-class notes, I used a subscript. So I did the outer radius minus the inner radius, and I used a subscript. I've also seen it where people denote the outer radius with a capital R and the smaller radius with a little r. And so either one of those is going to be fine. Now, last time I did kind of a more, I would say, algebraic approach. I would say I did a more graphical approach into solving for the radiuses here. This time around, I'd like to do a little bit more of an algebraic approach into solving for the radiuses. So for instance, if I wanted to find this inner radius here, this is going to be the distance between my axis of rotation, which is x equals 3, versus kind of the first time that I encounter the region that we're rotating. So in this case, it's going to be this distance right here, and this is going to be given by x equals 2, right? The straight up and down line here. So x equals 3 versus x equals 2, and I want to find the distance between those things. Now, certainly, again, graphically, you could just look at this and say, well, the distance between 2 and 3 is 1, right? You just literally ask yourself, how big of a step did I have to take to travel from x equals 2 to x equals 3? And that radius right there, that distance that you had to travel to get to our axis of rotation, which again, this is giving us some radius, we're rotating this around, right, is a distance of 1. So our inner radius here is going to be just a nice, simple 1. And notice, by the way, this does not matter on what the y value is. If y equals 0, our distance is 1. If y equals a half, our distance is 1. If y equals 1, if y equals 2, right, this radius does not change at all. That radius, that inner radius right there is always 1. On the other hand, for my outer radius, so my outer radius is how far do I have to go until, again, kind of I'm leaving this region here. It's the farther away one. So again, this radius is from our axis of rotation out to kind of this outer curve of our region that we're integrating over. Notice that this certainly is changing, right? And kind of the bigger y values you have, it ends up giving you a smaller radius. But again, we kind of know already that this is given, right? This equation right here is given by y equals x. And here we have x equals 3. And so if you want to know what is the difference between these things, again, depending on what your y value is, different y values will give out different radiuses. Again, you're just going to subtract. Just like before when we did 3 minus 2 to get our answer of 1. Now we're going to do, well, the largest thing here is x equals 3. And we're going to subtract away, well, it depends, right? Depends on what the y value is. So we could do 3 minus whatever the y value is. And again, y is equal to x. Remember, this is our inner radius. This will be our outer radius. So if you wanted to get this in terms of y here, here it is, right? 3 minus y is what our outer radius is. If you wanted to interject one more step, really, this is 3 minus x, and then you would trade in. We know y is equal to x, so you would trade that in. So remember, we're trying to do single variable calculus. Since we're integrating with respect to y, we want to get all of our variables in terms of y's. So in this case, right, we wanted to get everything in terms of y's, and we found here that this was 3 minus y. Of course, the first couple times that you're doing this, you should be paranoid, right? You should be paranoid that you made a small, silly mistake or something like this. So if you wanted to double check your work and make sure that this is true here, you could plug in specific values. For instance, if I was to plug in y equals 0, so y equals 0 is this bottom bit right here, and ask what is the radius? Well, at this height of 0, notice that we're going from the origin to x equals 3. That has a radius of 3. So plugging in 0 for y, that gives out the correct value for your radius. On the other hand, if you were to go up here at y equals 2, that's the very top of this, right? And if you were to plug in y equals 2, you would expect that your radius ought to be 1, right? Because you're at the point 2, 2, and you need to get over to x equals 3. That means you need to travel a distance of 1. So, and again, you can see if you plugged in 2 for y, you get 3 minus 2, that's 1. So yes, this seems to be working out correctly. So again, you can always kind of plug in some things in order to verify that you haven't made a small mistake. Now, at this point, we've done all of the difficult parts. And in fact, I've seen some, web work problems where they just have you set up. I've also seen D2L quizzes and exams, right? You can do these easy with multiple choice that just say, which of the following is the volume? And, they give you a whole list of things. And, one of the answers could be this, right? And this would represent the volume. So we've done the hard bit here. Now let's just quickly evaluate. I'm going to pull out the pi this time. So I see there's a pi in each one of these pieces. I need to expand this binomial, so you have to be careful and do the foiling. I know it's kind of tempting to just say 9 plus y squared and square each piece, but remember this is a binomial and you have to foil. You have to do the first, the inners, the outers, and the lasts. And so if you do it like this, you miss your inners, which happen to be negative 3y, and you miss your outers, which happen to be negative 3y. So you just did the first and the last, but you forgot the inners and the outers. And then we need to subtract away 1. Remember, I factored out pi from everything. So 1 squared is just 1 there. Let's do one more line of simplifying. So y squared minus 6y plus 8. So I've combined all of my like terms. Now we're ready to find the antiderivative. Y cubed over 3, 3y squared, 8y. Now we're ready to plug in our zeros and our 2's. Of course, when we plug in 0, we just get out 0. When we plug in 2, we get 8/3. Minus 3 times 4 is going to be 12 plus 16. This, by the way, is something that WebWork understands. So you could just type this into WebWork if this was a WebWork question. For D2L, remember, D2L doesn't understand expressions like this. So you couldn't do like 8 divided by 3 plus 4 in D2L. You need to plug this into your calculator and get a decimal equivalent. And that's what you would, if this was a quiz question or an exam question in D2L that they wanted you to find the final answer, you would plug this into your calculator to get the final result. All right, how's the chat looking? What are the big questions? Or not the chat, the Q&A. I apologize.
Yeah, I think there's a good one which asked the washer. The change, the washer method can be thought of as the change in the integral of the radius. Is it correct? And is the r in out the r ulterior minus the r interior analogous to the final minus initial? I think, yeah, maybe.
Yeah, these are I would say the answers, I believe, no to both of those cases. But really the devil's in the details. You have to be much more specific. So this is certainly related to something like the final minus the initial, right? But really these are complicated formulas with areas. And so, yes, it is as if you kind of found the solid volume of the entire thing, and then you drilled out some smaller volume right in the middle. So that's really what this is going on here with the outers and the inners. But even within there, when we found what is the inner radius and what is the outer radius, right? That's where I would say we really did the kind of the larger minus the smaller, or the final minus the initial, in order to get that distance. So again, I think the devil's really in the details for that. Let's see, let me scroll up here.
Someone is asking, could you also use 1 plus y for the radius? But I think that's no.
Sorry, one more time.
Yeah, they're asking about the ulterior radius, and then because you are using 3 minus y, and could you also use 1 plus y?
That would technically, if you did the integral setup like this, you would get the same answer. But this is actually, if you were to, like, structurally, this is if you were to take this and flip it on its head, because then you have the 3 here, and this is going to be 2 minus y. So then if you did the 3 minus 2 minus y, that would give you the 1 plus y. And so although they have the same volumes, they are different structurally. And so it's kind of maybe coincidentally, yes. And so you have to be careful. I have not been able to find any way to ever disable the chat. I looked a lot last semester. If you know a way to disable the chat, I wouldn't mind doing that at all.
Yeah, there's someone said there's a way, but I can't. You can go to audio settings. Maybe I can do it later, but now I'm too busy.
Oh, okay.
Let me
I
see.
guess here, attendee can
Audio.
chat with no one. There we go. I found it. It's in chat. There we go. No more chat.
Okay.
We'll see. Well, maybe we can make it, they can chat with just panelists. Here, I'll change that. You can chat with just us, but you can't chat amongst yourselves, I suppose. Okay, cool. So I would like to be able to do one more problem here, at least. This is the most difficult type of problem. And so I really think we owe it to ourselves. We may run over a little bit on this, but I think it's worthwhile. Even if you have to go, that's fine. I'll keep recording this and I'll post the video, and I would recommend that you watch it. This is one where our region, our solid is not generated by rotation, right? We're not rotating it at all. In this case, we have some interesting region, R, and notice that this one, we don't have a picture either. And we describe that, and then we glue onto it, in this case, squares. And the question is, well, if you glue on these squares, what is the volume of that solid? And so the first thing let's do is, again, I think a picture is very worthwhile in visualizing what we're actually doing. And also there's usually a time within the problem where it becomes very useful to be able to see how things are related. And so let's draw a couple pictures. Usually the first thing that I start off with is a 2D picture. And of course, you've seen a lot back here. We always started off with a 2D picture, and then we tried to make the 3D version. And so let's start off with our 2D picture. We have a region that's bounded by the parabola y equals x squared. So this is kind of some classic parabola here, y equals x squared, and y equals 4. So y equals 4, this is just going to be height 4 here, a nice, boring, straight horizontal line. And this right here is the region that it's talking about, right? The region that's bounded, or you could say trapped, by these two curves. So while there are lots of other regions, none of them are trapped by these two curves, right? So like this one over here isn't, while it touches both curves, right? It's not really trapped by the two curves, right? We need something that has finite area in order for it to be truly trapped. So now we'd like to take this and we'd like to come up with a three-dimensional structure, right? And so I prefer to, and again, this is X and this is Y. I'm going to try to take this and I'm going to set it on the table to some extent, right? So here's going to be some axes. So this is going to be maybe X and this is Y. And we need to have kind of a third vertical axes here. So I'm going to try to take this picture and set it on the table in order so we can actually visualize our 3D structure. So if we take this, and again, here's my x-axis and here's my y-axis, notice that this parabola opens in the positive y direction. So it's going to open kind of like this. And again, it stops at y equals 4. So this would be if I took this, and I'll even write the R like this so you can kind of see where it all translates to. This is if I was to take this and I was to take, you know, my piece of paper and set it down on the table. This is where what my parabola looks like. And so perpendicular to the y-axis, we're going to be gluing squares. So we could draw perpendicular to the y-axis here. So of course the y-axis, that goes up and down. And we want perpendicular to that, right? So perpendicular means at 90-degree angles here. We could also take and show that in the 3D picture right here. So again, we have our y-axis and we want to be perpendicular to that. And so these lines right here, right, squares are uniquely determined by their side length. So once we have this side length here, that perpendicular to the y-axis, right, we know how big the square has to be. Whatever that distance is there, that not only is the width, but it's also the height. And so you can see as we get bigger and bigger y values, these squares get bigger and bigger. Maybe this will be my last one right here. And so this is making some interesting 3D structure that has volume, right? And so the question is, well, what is the volume of this interesting 3D structure? And so, okay, two things. First of all, you can see that it brings up something about the y-axis, that we're perpendicular to the y-axis. So the y-axis has the equation x equals 0. So we are perpendicular to x equals 0. If you guys would please throw in chat for me, should we integrate with respect to x or with respect to y if you saw an x equals 0 equation? And yes, overwhelmingly, I see the correct answer, which is with respect to y. So even though that this is not a rotation problem, still the rule of thumb holds, right? If you see an x equals, right, and that's what you're perpendicular to, then you should integrate with respect to y. So at this point, we can now say what our bounds for our integral should be. Our smallest y value is at y equals 0 down here, and our largest y value is up here at y equals 4. So 0 to 4. Now, unlike with those rotation problems, we don't have circles, right? Before, kind of, when you have like rotating around, you get either full circles or you get circles with holes in them, right? And so that's why you have those corresponding area equations. Here, since we have squares, we need to use the area formula for a square. So the area formula for a square is just whatever the side length is, and you can denote the side length by the width, by the height, by whatever you'd like, right? You're going to take that side length and you're going to square it. And just as before, we're asking ourselves all of the same questions. So although the setup is slightly different, right, still kind of the overall roadmap for these questions is the same. And so the next thing that we need to ask ourselves is, how do I get all y's, right? How do I transform this, right? From previously we used r's, right? But how do I transform from side lengths of the squares to figure out how that corresponds to the y value? And so again, we need to go back, and I think probably the 2D picture is good for this, right? The overall side length of these squares is given by this purple line right here, right? This was the width of the square. And then of course we append, right, a height to it since it is a 3D thing, right? And of course we can see that for different y values as y grows. So for instance, if we do this y value right here, kind of the width, the overall width of this is smaller than if we let y be, you know, all the way here, right? If we let y grow and get bigger, right, the width of the overall square there is much larger. And so there's some interesting relationship that brings together these two pieces. And so notice that we don't, when we talk about the width, we don't go on forever. The width stops, right, as soon as we hit this parabola. And so maybe, right, and you can see the width is denoted somehow by the x value, right? It's horizontal movement. How far do you have to move left and right in order to hit the parabola? And so I think that it makes sense that we should be looking at the equation y equals x squared, right? And we want to solve for maybe the x here, because that has something to do with the width. And so if I solved for x and I just took the square root on both sides, I would get x equals the square root of y. The problem here, so if I just said, oh, okay, well here I have now my x values in terms of y's, and remember I was trying to get it in terms of y's here. So if I just said that this ought to be the square root of y, that right there is my width, then actually I'm going to get the wrong answer. Can someone tell me, how do I need to change this in order to get the correct answer? It's not root y. It's something else. I see the chat having several ideas. We have a brave soul who's raised their hand. Let's give this a go. Jacob, what do you vote for?
Wouldn't it be 2 rad y or 2 square root y because it's only 1/2 the radius?
Exactly.
Or 1/2. Yep.
When you take the square root on both sides, really you're finding the distance, the movement to go from the x equals 0 to the parabola. This right here is literally, you know, this square root of y right here. But you actually need to double it. And this, you can think about it in two different ways. You could either say that this is the square root of y. And this right here is when you take the square root, you ought to also have the negative square root of y. And so you should do the bigger one minus the smaller one, root y minus negative root y, to get 2 root y. So that's kind of graphically or really, I would say that's more algebraic. Or like you said, just with the graph right here, visualizing it, you can see that really whatever that X movement is to the right, you need to have that same X movement to the left. And so just by doubling it, because there's a lot of symmetry going on here, that would also work perfectly great. Excellent. Okay, so yes, that is how we would need to make this change. Now we have the bulk of the work done. That's again the hardest bit right there. Now let's go ahead and evaluate. So we're going to have from 0 to 4. When I take these things and I square them, well, take 2 and you square it, take root y and you square it. You can see that the integral here is not super challenging, right? The hardest bit is really the setup for a lot of these. So I do my antiderivative. I can plug in 4. So 2 times 16. And of course, when I plug in 0, I just get 0. And so my final answer at the end of the day here is 32. All right. So we'll stick around for another 5 minutes or so and answer any questions. A few last minute details before we start answering your questions is that I understand, right? There's lots of questions here, and kind of in general, this will be a trend throughout the entire semester, is that, I don't know, my eyes are bigger than my appetite, or however that saying goes, right? I always put on here too many questions, it seems, than we can realistically get through, because my dream is that we could get through them all. For those that we don't get a chance to go through, so example 3, 4, and 5 in today's class, I will write up solutions for those and I will post them on D2L, kind of right next to my blank notes. I'll have some filled in notes. So I don't have a link for that yet, but here later today, I will post and they'll have notes and then video. And then I think I'll probably just do filled in notes right next to that. And so I will do those extra problems. I would recommend that you try to do them on your own before peaking. See if you can do these problems. There's a couple of them that kind of come up in web work that I kind of stole from to some extent. So this I think is a good web work question. This also was a web work question. Or something similar to it, right? I have different numbers and whatnot and may have changed the problem slightly. But try to do those ones on your own, and then I'll post the full solutions to any problems that we don't get through on D2L, along with the video and all that sort of stuff. Okay, so we'll stick around for a little while and answer your questions for at least another 5 minutes or so. I do have a meeting at 3 o'clock. And so I probably need to leave at 2:55 to make sure I can join that meeting in time and all that sort of stuff. I'm going to stop the recording at this point.